Everyone expects HPLC to be complicated, but the reality is it's a bunch of simple things stuck together to make it look complicated. Just like you probably think your car is complicated to understand it mechanically, but that does not keep you from driving your car. So I'm going to demystify the HPLC for you today and show you all the components and show you that it's really just a bunch of simple things stuck together. So high performance liquid chromatography obviously starts with a liquid. So we're going to take this liquid, we're going to pressurize it and pump it over a column in order to do our separation and to figure out what's in our sample. So let's start off with the liquids. Up top, we have our solvent bottles, typically A and B. A in my world is usually water or aqueous. So in this case, A is water. We may add acid, we may add buffer, we may add a pH modifier to the water, but I still call that the water bottle, the aqueous bottle. And then the B bottle, in my case, is methanol. So B is going to be your strong solvent. In the HPLC world, basically you have two choices. You're going to do methanol or you can do acetonitrile. It's going to be one of those two. Yes, we have some exotic third choices like THF, but for the most part, all the methods, the vast majority of HPLC methods out there are going to be water blended with methanol or acetonitrile. In this case, I'm using methanol, and as you could tell, these are just atmospheric pressure bottles. So here's my water, and at the bottom of the bottle, you could see a little filter. So that filter is a glass filter. It's about a 10 micron porosity, and it's meant to keep particulates out of the pump. We're going to learn later on that if particulates get into your pump, it could actually do damage, some pretty significant damage. We want to avoid that. So in the bottle, at the bottom, we have our filter, and then coming off the bottle, we have Teflon tubing. So this is low pressure. I could stick my fingernail in there and make an indentation. So this is soft tubing, Teflon, which allows us to transfer the mobile phase from the bottle down to the pump. Now let me take the covers off. So what I'm using here is a typical HPLC instrument. This is an Agilent 1200 SL. This was Agilent's first introduction into the UPLC world, their first high pressure, ultra high pressure instrument. But let me take the covers off so you get a little better feel for what's going on. So we have our mobile phase. Now some pumps can handle up to 4 solvents, our quaternary pumps. We have about 12 HPLCs. About half of them are quaternary, half of them are binary. So we could have A, B, C, and D solvents. In most cases, you're going to use 2 solvents, A and B, and that's it. We could use others, but typically A and B. And so we have these coming from the bottle itself, and we're going to go into a degasser. The reason why degassing is very important is because our solvents, water, methanol, acetonitrile, at room temperature, room pressure, they have dissolved gases. Oxygen, nitrogen, carbon dioxide that are in solution right now in my methanol bottle. Now that's fine until we go to lower the pressure of the mobile phase. And what happens is when the pump goes to draw in mobile phase, it's a syringe and it pulls back, it applies a little bit of a suction and it pulls in mobile phase. When that happens, it will cause dissolved gases to come out of solution as tiny little bubbles. You probably know if you have a brand new bottle of, let's say 7-Up or some kind of a soda, when the bottle is closed, there's no bubbles. But as soon as you crack the top, as soon as you open it up, you see bubbles appear. Those are carbon dioxide bubbles that under pressure, carbon dioxide was in solution, dissolved in the liquid. And as soon as you lower the pressure, those bubbles come out of solution. So if that happens in your HPLC pump, that's going to cause problems. So what happens is if your mobile phase is not degassed, as your pump draws in solvent right here into the inlet, it will then cause these bubbles to come out of solution, and a bubble drives your pump nuts. It doesn't know what to do with it. Bubbles are compressible, liquids are not. So bottom line is you never want to get a bubble in the pump. It's just going to give you a headache. It's going to be you're going to spend a couple hours getting rid of it. So how do we avoid that problem? We remove the gases at their source. So we're going to take water, methanol, acetonitrile, whatever you're using, and we're going to pass it into a vacuum chamber. So what you can't see behind the scenes is this piece of tubing. So let's follow the methanol line. So methanol is going to go in to here. We have 4 channels, A, B, C, and D. We only need 2 because we only have 2 solvents. So we have the methanol going in, and when the methanol comes back out, it has been degassed. It's going into a vacuum chamber, And there's a bundle of tiny little tubules. So this 4mm piece of tubing breaks up into maybe 50 tiny little tubes. They have very high surface area and they are semi-permeable. It's a material called Axion, which means it's got tiny little holes that are big enough to allow gas molecules to escape, but not liquid droplets. So by the end of this, we'll call it long piece of tubing, this tiny little tubules, by the end of this, all the dissolved gases have been removed. They've come out as bubbles. They get pumped out. You can hear a little vacuum pump in here. They get pumped out, and at the end of this piece of tubing, it's coming out of the degasser, we have pure degas mobile phase. So coming out of one side, the A channel, I have pure water. The B channel, I have pure methanol. They've gone through degassing. What you can't see behind the scenes is in this version, there's 1 to 2 milliliters per channel that is behind the scenes. So if you ever change your A bottle, so if you go from a phosphate buffer to an acetate buffer, remember, not only do you have to pump out the lines, but you got to pump out the volume that's inside there as well. Okay, so now we have come out of the degasser. We have now freshly degassed mobile phase. There's no dissolved gases. So now when we pump them, when we draw them into the pump, we don't have to worry about that bubble formation. Number one cause of problems in HPLC, hands down, is air bubble in the pump. Air bubble gets caught in the inlet check valve, and there's a little ruby sphere in there, and it floats it high. And when that happens, we get pressure fluctuations, and the pump just doesn't work the way it's supposed to be working. So we want to avoid that by using the degassers. In the olden days, we didn't have degassers when I was a kid. We used helium sparging. So you bubble helium through the mobile phase. Works great. It gets to be expensive because you got to use helium. But we also had offline vacuum degassing where you take your bottle and you put it in a vacuum, like a water aspirator or maybe a stirring bar. That is not very efficient. It's a terrible way to go. If you have to do it, if old-fashioned, you do it. But with a modern degasser, you don't have to do anything to the mobile phase before you put it in the bottles. So now in this pump design, like I said, there's a couple of pretty common pump designs out there, and all the manufacturers share a lot of similarities. Of course, that would make all my friends mad at each of the different companies, but for the most part, a Ford and a Chevy and a Mercedes all have the same general design on the engines. So in this case, this is called a binary pump. There's two styles of pumps, binary and quaternary, or low pressure gradient, high pressure gradient, or what their official names. So this is what's called a high pressure gradient. It refers to where we blend the mobile phase. So low pressure gradients are still high pressure pumps. It just means a low pressure gradient means we blend on the low pressure side, the plastic tubing side of the pump, and not the high pressure side. In this case, it's called a high pressure gradient because pump A pumps pure water, nothing but water. So pure A comes off of pump A. Pure methanol comes off of pump B. So the two are then blended, and I'll take you through the flow path, but they're blended. There's a T right here where the two are blended together. So if I want to run 50-50 methanol water at 1 ml a minute, I would set pump A to half a ml a minute, pump B to half a ml a minute, and then the output is combined to give 50-50 methanol water at 1 ml a minute. So you get the idea. Fortunately, the pump does the math for us. We just tell it the percentage, and it figures out how to make that happen. So let me take you through the flow path. This would be like opening up the hood of your car. We're going to take a look at the engine, and I'm going to point to the different parts, and we're going to sort of figure out what each part is doing. So I've told you that we've come into the pump. Here's my A line coming into pump A. It enters into what's called the active inlet valve. So this is the inlet check valve. In the olden days, this were just a passive check valve like the one up here, but this one is actually activated. So you think what a check valve does. It's a ball and seat, and the ball can move up, but when it pushes down, it locks any kind of backflow. So it allows flow to one direction, but not the other. So in this case, the flow is limited to going up into the pump. We don't want to pressurize this and squirt it back in the bottle. We want to make sure we squirt it up out of the pump. So piston number one, this is a sapphire piston. And what it's doing is it's sort of back there. There are two pistons, pistons 1 and 2 are pushing back and forth. And you can imagine that like a syringe. So this syringe is filled with 100 microliters of liquid, and then the piston pushes in, displaces it, and then pulls back, refills, pushes back. So that's what's called a reciprocating piston pump. Just about every pump on the market today, I think every pump on the market today is a reciprocating piston pump. So this piston draws back, And then when it pushes forward, the inlet valve locks closed, the outlet valve opens, and it pushes mobile phase out the outlet valve. And this is just based on pressure. If I put enough pressure on this side, I can push up. If I put pressure on the other side, remember, it's gonna close off. So now I have high pressure flow coming out of piston number 1, and if you could see, I have stainless steel tubing. This is now high pressure. So from here, it's a little hard to follow, but this piece of tubing actually dips down underneath the pump head and it enters into piston 2. Now, if you notice this coil of tubing, this is great to see this because this is very old school, which means it's tried and true and it works great. And this is a pulse dampener. So pulse dampener, you think about this piston is going forward and back, and so high pressure, low pressure, high pressure, low pressure. Well, this pulse dampener will expand and contract just to absorb those shocks. So like the shock absorber on your car, you have a very bumpy road. It doesn't get rid of the bumps, but it smooths them out. So this removes the vast majority of the pulsation from piston A before we go into piston B. So piston B is pumping, and then coming out of piston B, it comes out the front of the pump. Now, if this were a quaternary pump, we'd come right out of the pump with our blended mobile phase, we'd go to the autosampler. But at this point, remember, it's not blended. This is just the pure 100% A. So we're coming off here. Now, it takes a little bit of an extra path because remember, we now have to blend it with what's coming out of B. So whatever I said about pump A, the exact same thing is happening in pump B. 2 reciprocating pistons. These guys are pumping methanol. These guys are pumping water. The 2 come together in this T. So 2 come in, 1 come out. So this one that comes out, it's a little hard to see this. This is this really small capillary tubing. You see a little green piece of tape on it. So it's this coil, and what it's doing is, so this is the output. At this point, we could then take it to the autosampler to get our sample, but the folks at Axion, they're very nitpicky about the way the pulsations work, so they're gonna remove even the tiny little pulsation that's there. We're gonna remove it. So we go into a pressure transducer, let's measure the pressure, and then out of the pressure transducer, we go into the pulse dampener. So pulse dampener is this thing that sometimes called a hockey puck. It's just sort of round and flat with a hockey puck. It is filled with a compressible liquid, like a nitrogen shock absorber on your car. And again, it's going to take the big pulsations and then make them smaller. In this case, it's going to take the small pulsations and then make them even tinier. I think we get like a 98% reduction in the pulsation going through there. So we go in the hockey puck, we come back out, and at this point, the tubing goes to the back of this purge valve, and we are now ready to start the chromatography. So all that I just talked about essentially can be summed up by saying, I got 2 pumps. Pump A, pumping pure water. B, pumping pure methanol. I can control the 2 flow rates. I can combine the outputs, and I can get any blend I want. You want 0%, you want 0.2%, you want 12.7%, any percentage you want can be blended with these 2 very high precision pumps. This design is more expensive than what's called the quaternary pump because we have 2 high pressure pumps. These are the expensive parts of the instrument. You can imagine the machining that goes on to make these things so reproducible. Okay, so now we have mobile phase coming out of the pump, and this is the high pressure line coming out. Again, it's capillary tubing. Axion likes to use the really small outer diameter tubing, but this is running high pressure. This instrument will go up to 9,000 psi, so this tubing will hold that kind of pressure. So now my mobile phase, the next step is to pick up the sample. So we're gonna go down to the autosampler. I'll pop this guy open, and this is the tubing. I don't know if you can see. Here's coming from the pump. It's going to the autosampler, and the autosampler, its job is just to insert the sample. So imagine we have this high pressure flow going through this piece of tubing. We would like to just insert our sample into that and allow it to transfer to the column. Now in gas chromatography, it's simple. We have a little rubber septum, and we can stick a needle through the rubber septum because the GC is operating at 10 or 20 or 30 or maybe 50 psi. We're now operating at 9,000 psi. We cannot stick a needle into that 9,000 psi because we couldn't hold back the plunger. So we need to isolate the high pressure and the low pressure part of the instrument. So I got high pressure flow coming from the pump, coming through this piece of tubing. It enters the injection valve. So every autosampler in the world has that same injection valve made by Rayodyne. It's a fantastic valve. And what it does is it connects a piece of tubing, one fitting, to the fitting next to it. So what we have in, there's two modes of the autosampler, load and inject, or also called main pass and bypass. So in the main pass mode, we have high pressure flow coming into the autosampler, and it connects right next door. And when it connects next door, it connects to the left, this blue piece of tubing. This blue piece of tubing enters what's called the metering device. It's going to measure our sample. It then goes from there around. It then becomes the needle, which is right behind this. I'll lift that up a little bit so you can see behind that is a little needle. And the needle is now part of the flow path. It's connected to the needle seat. There's a little capillary underneath called the needle seat capillary, and then it connects back to the valve. So why am I telling you all this detail? Because we have this high pressure flow and we need to insert our atmospheric pressure sample into it. How do we do that? We start by taking the autosampler offline, rotating the valve. And by rotating the valve, we're going to take the high pressure flow, go to the valve, and we're going to connect right next door, and this is going to go to the column. So in that mode, what's called the bypass mode, or the load mode, it allows us to take high pressure flow, go to the valve, bypass the autosampler, and go to the high pressure flow, go onto the column, and then the detector. That keeps the column happy, keeps the detector happy, nice stable flow. So during that time, we could then lift up the needle will go to the vial, draw a sample up, reconnect, and when it reconnects, all we got to do is rotate the valve just a sixth of a turn to connect the flow coming in, going through the autosampler. So imagine, flow comes in, it could go straight to the column, or it could go through the autosampler and then to the column. That's what the injection valve does. Now, the injection valve has a lot of intricacies into it. I have a separate video on that, so if you want to see the details, check out my detailed explanation of the sample injection valve, because on the inside, there's one part that's going to wear out, and the whole autosampler is only one piece you'll ever have to change, and that's the rotor seal. And when I do the deep dive, I'll explain why it goes bad, and I'll show you the little pictures as well. Okay, so now we have the sample. We have a high pressure flow. We have a sample, there are 5 microliter sample in there. The next piece of tubing is going to take us to the column. So at this point, I could simply, so this is our red piece of tubing coming out, I could simply attach to the column. By the way, this is my, this is my HPLC column. 5 centimeter, my favorite column length is a 5 centimeter, 1.8 micron UPLC column. This is my Agilent Zorbax Eclipse Plus C18, my favorite column. It's going to do what you need to get done for most applications. So we have this high pressure flow entering this red tubing. Instead of going directly to the column, the folks at Agilent, they're a little nitpicky. They want to make sure that the temperature of the sample is the same as the temperature of the column. You know, the sample is at 20 degrees Celsius, the column's at 40 degrees Celsius. We don't want to have a temperature gradient across the column because it causes a little bit of noise. So it's nitpicky, it's a small amount, but let's get rid of the noise. So what Agilent does is they go through this heating block first, and it's 3 microliters from here to here. And then coming off here, we now have the sample, the mobile phase, the column are all at the exact same temperature. So the sample now comes through here, travels through the column. Here's where the magic happens. This is where we're going to do the separation. And then coming off that column, after we've done our beautiful separation, we now need to detect the molecules. How do we detect it? Well, just as in GC, we have a lot of different detectors in the LC world, but we have one that dominates, and that's the UV-Vis. So UV-Vis detector, there's different flavors of it, is what I like to call it. There's different types of it. There's the fixed wavelength UV-Vis. Those are not very common anymore. There's the variable wavelength, which are really common. There's a multiple wavelength, sort of common. And there's the diode array, which is what this is, which is also a very common, my favorite design. So all these UV detectors basically work the same way. We have a really bright light. So if I open up this, we've got a really bright light bulb on the left side of the detector. This is a deuterium lamp. It's filled with deuterium gas. So really high intensity light is coming off of here. It goes through a flow cell, and the other side, I have a detector. So this detector is going to count the number of photons that go through. So if a sample, an analyte, is flowing through the detector, if it absorbs UV light, the number of photons is going to drop. Since we measure absorbance, we flip that upside down and we see our peaks. So I could show you what it looks like. If I open up this little door, the flow cell itself is self-contained. So if I pull it out, there's flow going through the instrument right now. We're running a low flow rate, 0.2 mils a minute, but there's flow going through it, but nothing's going to come dripping out because this is a self-contained little piece. So if we look at it and try and understand the design, it's a really simple design. This detector cell is like a block of stainless steel, and we drill a hole in the middle, and we put 2 quartz windows on the outside. Not glass, but quartz, because glass absorbs UV light. So quartz windows on each side. The flow comes in the top, goes down the path, and then goes out to waste. So we shine light in here. We measure how much light is absorbed by the sample. This Z flow is useful because if we measure in the direction of flow, we get less noise. We don't like to measure across the flow. So this essentially is a cuvette, is a flow cell that allows us to measure the absorbance of light of the analytes running through. Now these flow cells are very small. 13 microliters a standard flow cell. You can easily get a half microliter flow cell and get smaller if you need, but they're very small, which means they introduce very little broadening or very little loss of efficiency in the instrument. Now, if you look inside, I don't know how well you're gonna be able to see this, but if I put my finger here, hopefully what you're seeing is a little bit of light bouncing off my finger. I don't know, you might not be able to see it, but I guess trust me on this one. There's a little light back there, and that's the UV light. So it's coming through, it goes through the flow cell, and then the detector's on the other side. So this guy, put this guy back in. There we go. So if I close it back up, the instrument now, the flow is continuing through the flow cell, and then from the flow cell, it then goes out to the waste bottle. So that is essentially the entire HPLC instrument. Took all the covers off, showed you sort of the nitty-gritty on the inside. I'm going to do a deeper dive into the pump in terms of the pistons and the pump seals, and show you how to change those. And I'm also going to do a deeper dive on various parts of the instrument, including the injection valve.